Hello and welcome to this lecture. Thank you for joining once again. My name is Dr. Zulfikar Kassam. I'm glad to have you join me here. And it's glad to hear for some of you who have been emailing me. I'm also very happy to hear that people are coming from different parts of the world, which is beyond the North American continent, which is great to hear. So thank you for joining. Keep those emails coming, keep those requests coming. Once again, as I mentioned, if you do need the slides, I am happy to email you the slide deck. Okay, so we're trying to start a new section this time around. Okay. So this section is going to focus on digital signals. All right. Now, the focus right now or the discussion today is going to be about data transmission from computed data to network signals. One thing we do have to understand is the nature of computer data. So we're focusing on this part or this part of the slide right here, the nature of computed data. So as we know that the computer stores and processes all information in digital format, right? A binary system of ones and zeros. So this is what the computer knows, and this is how information is stored in the computer. Okay. So the high voltage plus 5 will be binary 1, and the low voltage, right, almost 0, will be binary 0. So this is how the computer actually stores this information. Now, looking at why conversion is necessary, you can imagine that while the computer speaks in binary, the physical world of networks is a lot more complex. So different transmission media have their own physical properties and limitations. We can think about impedance limits, right? Something that's going to impede that signal from going through. There'll be some attenuation in the signal as well. So we need to say, as this signal travels, the amplitude of that signal or the power of that signal will be reduced as it moves along. There'll be some bandwidth limitation as well, depending on the type of media that is being used to transport this information. Plus, we will have to deal with some noise and interference from different sources, right? So raw binary data cannot simply be pushed onto this media without encoding or conversion. Meaning to say encoding or conversion is necessary in some form, right? To change this digital media format into a signal that can be transmitted over. So data must be transformed into a signal that is compatible with the chosen transmission medium and that can travel reliably over distance. Now, this is where the distinction between digital signals and analog signals becomes critical. Now, let's try and explore this transformation process, right? Let's look at the transformation process here. The computed data is binary in its format. This information needs to be encoded or modulated in some form to create a network signal. This network signal may be analog in nature, as you can see, like some form of wave over here, or it could be actually digital as well, and we'll look at all these different ways in which data is transmitted, whether it's analog or digital. And then this information, this signal, is sent over the transmission medium, whatever that happens to be, and we will look at that here at the bottom of the screen. You see some examples. We'll talk about that. So the idea here is binary data is encoded and modulated into a signal that is sent through a transmission media. Now, we have to also appreciate and understand that this signal that we create could be analog or digital in nature. If it is digital in nature, it will constitute of discrete levels, which means it takes on a finite set of discrete values. We will talk about digital signals in a later course today we will focus on the analog signals part, but let's continue on from where we are. Or it could be analog signal, which is a continuous waveform. Okay? And we'll talk about how that works and which media uses what type of signal. So the analog signal varies continuously over the time and amplitude. Okay. Now we look at copper wire, for example, electrical signals over copper wire, right? Like this electrical signals are sent over Ethernet, could be DSL as well, right? In fiber optics, light signals over glass fiber, right? So the glass fiber can be used, right, as a transmission medium, and which will basically allow light signals in terms of ones and zeros. So for example, a pulse of light will be 1, and if there is no pulse, this will be interpreted as being a 0. In wireless communication, the signals we have here that can be used would be analog in nature, in the form of some form of radio waves, right? So if we are traveling here between our location and the satellite, for example, or even Wi-Fi within our own home, or to the cellular transmission media, right? Or cellular towers, we'll have to use wireless. And in terms of wireless, we'll have to use radio waves, right? To basically transmit information over the air. Okay. So we look at, and now of course here in this particular case, we will have to use analog form. So we'll have to convert this computer data in some form of analog signals. And we'll look into the details of how that actually works. So the key takeaway from this slide is data inside the computer is binary in nature, and to travel across any network, it must be encoded or modulated into a signal that matches the characteristic of the transmission medium in order to ensure reliable communication. Okay. Now, digital versus analog signals. Now, digital signal is one that represents data using discrete, distinct states, most commonly 2 states, corresponding to binary 0 and 1. When data is transmitted digital, the signal switches between defined voltages or light levels, right? So as we discussed, for example, a high could be positive 5 volts and a 0 could be no voltage at all. In some cases, it may be even minus 5 volts. We will look at the different ways of how data is encoded in a later lecture, right? In the wide example, for example, Ethernet, right? Voltage pulses are being sent over the copper cables. The encoding system defines how transmissions or transitions represent zeros or 1. There is the Manchester encoding scheme. There is the non-zero to return. These type of encoding schemes are some things we'll go into a lot more detail in subsequent lectures. In the case of fiber optics, for example, digital signal takes the form of pulses of light. Light on will be a 1, light off will be a 0. Now, the good thing about digital transmission is that it's more resistant to noise, right? Because if there is noise, usually the plus 5 volts could be, let's say, 4.9 volts or 5.1 volts, which is easy for the computer to decipher that it is still considered as being a 1. So it's more resistant to noise and carry more data at higher speeds. However, the only concern here, or the only limitation, it is preferred for shorter distances and modern wired networks. So now we are constrained with shorter distances and modern wired networks. So mind you, the only exception is the fiber optics, which goes over thousands of kilometers. There are cables under the sea which basically are up to 12,000 kilometers long, hard to believe, 12,000 kilometers long, which transmit optical signals. Mind you, these optical signals still have to go through repeaters to enhance the signal after a certain distance, after a certain number of kilometers. We will have to enhance the signal once again. So it won't go 12,000 kilometers without any intervention. There will be some intervention to re-energize the signal. So now let's look at why conversion is necessary. So digital data, which is hosted by the computer, must be converted when transmitted over analog media such as telephone lines or radio waves, right? Because these media carry continuous signals. Right? So the digital data needs to be modulated by the modulator into an analog signal, which can then be transmitted over the air, right, wirelessly. And then finally, at the other end, it is demodulated and converted back into digital data. Now, in a simple format, you can think of three different forms of modulation. There is amplitude modulation, in which you see different amplitudes being used to encode data, meaning different data. So different amplitudes will represent either a 1 or a 0. So different amplitudes represent a 0 or 1. Then there is frequency modulation. In frequency modulation, you have different frequencies representing zeros and ones. And then there is phase modulation. In here, there is a phase shift in the wave representing a 0 or 1. So a normal sinusoidal wave, which is fully in phase, will be considered basically a 1. And if it is out of phase, it'll be considered a 0. Right? So we look at those aspects later. At the receiving ends, the modem performs the reverse process called demodulation, which basically converts the analog signal back into digital data that the computer can understand. Okay. Now the analog signal is continuous in nature, which is a wave-based signal that varies smoothly over time. It is characterized by three different properties. Its amplitude, which is the height of the signal. Then there is the frequency, which is the number of cycles that it completes in 1 second. This is measured in hertz. And the phase, which is its position in a cycle. Now, we have covered before in previous lectures, if you like, you can refer to it in terms of the phase angles of different waveforms. So traditional telephone lines and radio waves are examples of analog media. So the height is the amplitude, as we mentioned. The number of cycles designates the frequency, and the phase is how much, or the waveform where it is at time 0. So as we mentioned before, so just to repeat the same thing, is that when digital computer data needs to travel over an analog medium, it must be converted into an analog signal through a process called modulation using a device called a modem, which is really a short form for modulator demodulator. So the key takeaway here is digital signals are discrete and robust, ideal for modern wired and fiber networks. Analog signals are continuous and natural, essential for radio and legacy systems. Modulation is what is required to bridge the two worlds together, enabling communication across all media. Okay. Now, when we look at wireless transmission, so this is going to be more our focus in this lecture and subsequent lectures. So this is the last slide for this specific lecture. And basically, wireless networks such as Wi-Fi and mobile networks also rely on analog radio waves as their transmission medium, right? The digital data from the computer is modulated into carrier frequency or carrier radio frequency for transmission through the air, right? So when we look here, for example, your computer is hosting this digital data, right, which is in the binary form, which is modulated, right, into some form in here, QAM. We'll talk about QAM later on in a lot more detail than what is shown in here. But right now, let's just kind of go into the details later. But it's a modulation form. QAM is kind of the more sophisticated form, which we'll look into in a subsequent lecture, and which is sent over the wireless medium, which is basically radio waves, and then demodulated at the other end into digital data back once again, right? So the end-to-end picture here is the computer data, which is in the form of digital data. It is encoded, right, or modulated, converted from binary into suitable signal transmission, right, which is, in our case, in the terms of wireless, it's going to be analog in nature, not digital here. This is just an example in here, but it is encoded, transmitted, decoded at the other end into binary data. It's important to understand the choosing the right transmission. So the choice between digital and analog transmission depends on the type of medium, whether it's wired. Wired tends to normally use digital signals, while wireless tends to use analog signals. Fiber can use digital signals, right? And the radio will use analog signals. The distance involved also comes into play, right? The short range, you'll use copper wire for short range. For long range, you'll use either wireless, or if even longer range, will be fiber optics, right? And of course, you can use satellite as well, which is very long distance as well. The required bandwidth is very important to consider as well, because this will determine how much data that can be transmitted over. And the cost of the infrastructure becomes important, right, as well, because this will be affecting your deployment and your maintenance consideration. So the key takeaway here is in that in modern networks, the trend is strongly towards end-to-end digital transmission wherever possible, with analog conversion occurring only in legacy infrastructure or wireless media, right? So digital is preferred, but analog will of course be needed because there's lots of wireless communication that will happen, be it satellite, be it just normal wireless networks at your home or in your office or you're in your enterprise, or it could be wireless through, of course, these cellular networks, right? So thank you for watching today. I hope you can join us next time. I hope you enjoyed this lecture, and please give me feedback about how you enjoyed the lecture and the slides. So I'm trying to use a lot of AI basically to create this wonderful slide. It takes a lot of time. It's not perfect, so it takes a long time to create this size slides in this format. But I hope you are liking this slide format much better, I'm hoping. Please give me your feedback whether you like the traditional slides that I was using before, like hand created all the things, but now I'm using a lot more AI in my slides, and I'm hoping you like those slides. Thanks so much for watching. Take care. God bless. Have a wonderful day and a great week as well.